Alright, in this video we're going to talk about Unit 3, Objective 1, and that's going to be area with geometry and then basic integral rules. So recall from Unit 1 that the integral of a function gives the area under the curve. So area under the curve between two x values. Now, the integral of f of x from a to b, remember it looks like this. So the integral from a to b of f of x dx. Now, also we need to recall that Riemann sums used rectangles to approximate the area under the curve, and the more of them that we use, the closer our approximation is going to be. So in an ideal situation, we're going to use infinitely many rectangles to get an exact area under the curve. Now, in order to do this, we're going to need to use the area formula for a square, for a rectangle, and the idea of a limit that we don't really have yet, but we can kind of fake our way through for now. So what we're going to talk about is the fact that the integral from a to b of f of x dx is going to be equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of c sub k times delta x. Now, this is a whole lot of stuff and it looks really, really confusing, but it's not that bad. So what all this stuff means is this is a bunch of y values. Right, f of any point is going to give you a y value on the curve. So this f of c sub k is just a y value. Now the c sub k just means k is going from 1 to infinity. So we're picking one arbitrary point, and then we're going to take infinitely many more of those arbitrary points. So this is just making sure that we have infinitely many y values. And this delta x is still just the change in x values. So it's going to be the distance from from c sub 1 to c sub 2 to c sub 3. This is just going to be how much that changes. So if we think about y values are up and down. Change in x values are across. Well, if I multiply this by this, I'm really finding the area of a rectangle. So this is just a fancy way of saying take infinitely many rectangles between two values a and b. So the first thing that we're going to do, and probably not going to show up on AP, but it has once or twice, is to take that sum and try to write it as an integral. So we're looking at the limit as n approaches infinity of the sum from k equals 1 to m, or n, of 3 times m sub k squared minus 2 m sub k plus 5 times delta x as an integral over the interval negative 1 to 3. So the first thing we want to think about is if we're writing it as an integral, we need a little integral sign, and we need our limits of integration. From what value to what value? Well, they tell us those values here, so we're going to go from negative 1 to 3. And if we think about what this is, on that previous slide it said f of c sub k. So we're plugging c sub k, or in this case m sub k, into some function for x. Well, that just means all we have to do is take all those m sub k's and turn them into x's. And then our delta x turns into a dx. The other thing that's going to change as far as delta x turning into a dx, this sigma here is the Greek letter s. This is an s, so it kind of turns into not a Greek s, but the s that we're used to seeing for sum. But all we have to do is take the arbitrary point and put an x in, throw it into our integral, and that's all that it's asking us to do there. So the other thing we want to talk about in this video is integration rules. So we don't know how to integrate yet. Those are coming. But what we can do is use graphs of familiar functions in geometry to find area under the curves, and then we can manipulate those with these two rules here. So before we talk about these rules, I want to kind of mention what I mean by familiar functions in geometry. If I were to ask you to find, say, the integral from 0 to 2 of the absolute value of x. We should know what the graph of that looks like. So if you were to graph that, the graph of the absolute value of x looks like this. If you were to integrate just from 0 to 2, we'd only be looking at this area here. And using geometry, we know that's a triangle, so we can find the area of that curve. So that's what I mean by familiar functions in geometry. Something you're going to have to graph and then use one of your geometry formulas for area to figure out the area under the curve. So basically everything is going to be straight lines, or it's going to be like a circle because we know the area of a circle. But how we're going to be able to manipulate those, there's two things that we're going to talk about. First, the sum and difference. So the integral from a to b of f of x plus g of x dx is going to be equal to the same thing as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And this is mostly going to be used when g of x is a constant. So something like f of x plus 4 is when we're mostly going to use this. And then that f of x, or plus 4, the integral from, say, a to b of 4, well, we know what the graph of 4 looks like. It's just a horizontal line, so we can use geometry to figure that piece out. The other one's going to be the constant multiple rule. If you're multiplying, say, the integral from a to b of c times some function f of x, where c is a constant, we can pull that constant out front of your integral and say the integral, or c times the integral from a to b of f of x dx. So let's look at one example real quick, and then we'll call it quits on this video. So what we can do here is it says if the integral from 2 to 5 of f of x dx equals 18, then what is the integral from 2 to 5 of f of x plus 4 dx? Now, we don't know what f of x is. We can't graph it, we don't know, so we don't know what the graph of f of x plus 4 looks like. But what we do know is that that integral is going to be the same thing as the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 4 dx. And if we think about this one here, we know the graph of that is simply this horizontal line. And if I want to look from 2 to 5, the area under that curve, well, we have a rectangle. And we can find the area of that rectangle. We know that this is 1, 2, 3. So the base of that rectangle is 3. We know it's 4 high. So the integral from 2 to 5 of 4 is going to be equal to 12. Right? Because 3 times 4 is 12. They also already told us that this piece here is 18. So we now know that the integral from 2 to 5 of f of x plus 4 with respect to x is going to be equal to 18 plus 12. So the area is going to be 30. So that's how we're going to use these rules. We're going to break them up into something that we can find, even though we don't know or integral rules yet. And generally, they're going to tell us something about f of x. So that's going to do it for this video. We'll see you in the next one.